Okay, hello everybody. So I'm really excited to bring you this today, and this is the reason that we went into a signature scheme with efficient protocols in sort of the theoretical aspects in the previous sort of set of videos, is so I can show you and hopefully you can have a better understanding of this example I'm going to show you and is included in the tutorials that you're going to go through yourselves. So for me, when I got this to work and I parsed the data and pulled out the cryptography aspects of it, it was a real eye opener, and it's just really cool to see something like this, all the way under the hood, and to have an appreciation of kind of the complexity that has been enabled and is enabled by Hyperledger Aries without you needing to know about these signature schemes in too much detail. I think it's a real achievement of this code base. I'm looking forward to the future iterations of this as we move into a world where BBS Plus becomes a default standard. But, I want to just show you this. I think it's really cool. I hope you like it. So the first thing to be aware of is the key generation process, right? To sign anything, we need to generate a public and a private key. We need to share our public key with the world or with anybody who is going to want to be able to verify the things that we sign. And, a signature scheme with efficient protocols is no different there. We still have to do this key generation phase. So let's look at how that works, right, in the example that I have for you. So this is the set of notebooks that you will be working through, or maybe you already have worked through. I just want to highlight what's going on here. We're identifying three schemas. So these schemas are written to the sovereign staging network. And we're saying to our agent here that you've initialized on your machine that we want to generate public and private key pairs that allow us to issue credentials against each of these schemas, right? To sign statements that are, meaningful based on these schemas. So I'm just going to run through this and I'll show you what I mean. It takes a little bit of time because what it's doing is it's going through this key generation process and getting large cryptographic numbers that meet the properties of this scheme. And it's really one of the problems of the CL RSA scheme is that this process takes a bit longer than is maybe acceptable in a modern system, which is why we do this key generation stage once and the public keys are then written to the public network. So there you go. Okay, so we wrote three schemas then, and maybe it took, a minute or two, but still, it's not too bad. And I'm just going to show you this. Now, I don't know if this is bad that I've written these things to the sovereign staging network, and you will be doing so too. If it is bad and not frowned upon at least, then we can change to a different network. But I think it's quite cool because we have this indie scan thing, which is, we've just done something on our local machine. We created a public and private key pair, and then we published the public key pair to a public network that other actors in this system can access without having to talk to us, the issuer. So you can see here, it's pointing to some information, it's linked together. And the first thing I want to show you is this. This is the transaction we wrote. You can see here, this is a public key infrastructure, right? It's saying this is the signature type CL, and this here, all this large thing is the public key. So it's a lot of big numbers. And these map to the signature scheme, right? And this is why it took so long, because we had to generate these numbers, and each of these numbers has to match a certain criteria defined by the signature scheme. But what I want to point out here is this R, right? This R is, for this signature scheme, we've generated a random, unique number that allows us to sign an array of messages that represent the date, the master secret, or the name, right? So instead of it just being a signature on a single blob of data, we've broken up our ability to sign each blob of data, each attribute in this case, in the credentials setting, each attribute individually. And that's really powerful because it means that they can individually be revealed or hidden. So I think this is quite cool. It's cool to see the data, always. And, the fact that we pointed to a schema when generating this credential, this public key, is how we identify the number of attributes that we need to generate a public key for, right? So for every new attribute, we would have another R in this array, another array of R, right? So like if I had a, last name attribute, we'd have another big number that we'd have to generate. Okay, in the next section, I'm going to show you how you can see that this credential gets issued and how you can see the information that flows backwards and forwards between a holder and an issuer in that case. Okay, so next we're going to have a look at credential issuance, and I've just skipped a bit further on in the tutorial series and I've run through the code and we've got some output, and I really just want to go over that output and really highlight it to you and explain what's going on there. I think it's a really powerful way of looking at the cryptography that happens under the hood. And if you're not interested in this, completely up to you, but as you run through the tutorials, this output will be there for you to look at yourselves. I just want to dig into it a little bit now. So we're in number 6, onboarding a data owner, and the holder, the issuer, the OpenMind issuer has created an invite for the data owner to accept. Once the data owner accepts that, then the OpenMind authority will engage with the issuance protocol to issue them a credential that attests to them being a data owner. And we've done this, we've accepted the connection. And the aspect that I really want to highlight is this all the way down here, right? We're looking at basically messages that are sent and received by the holder of this protocol, right? The role of this agent is in the holder mode, and they're sending and receiving messages between themselves and the OpenMind authority as they engage in this protocol. And every time you see one of these, that means a message has been sent or received. So the first one is received. We've received an offer from the OpenMind authority. They're offering to issue us a credential with these attributes in them. And they're also proving to us that they have a key that can issue this, right? They have a valid key able to issue credentials against this schema. In addition to this, they include a nonce. And this nonce is then used by the holder in this role. So the data owner is going to use this nonce to create a commitment to their master secret and prove that this commitment is valid, right? That they know the master secret that they claim to have committed to. Right? So yeah, as you can see here, we're hiding the master secret because we don't want to disclose our master secret, but we want to commit to it so that the issuer can sign it as part of the credential. And then we can unblind this later in the protocol to get a set of attributes where we know knowledge of the master secret and can use that to prove us in the future that the credential was issued to us. Okay, and as I said, we do a zero knowledge proof that proves that we have created a correct binding. Okay, keeping going. So this is credential received now, which is once the issuer has verified this proof, they're going to sign these set of attributes, and they're going to send that signed set of attributes as a credential over to us. So you can see here they have saying this is the schema, this is the credential definition, these are the values that we're offering you, or that we've issued you rather. Right, so you can see domain, we have this raw thing, healthcare, and then encoded. So encoded is like they're turning it into a mathematical number that can be used in the proof. And again, name is will and encoding. But then there's the signature value, right? And I think I've broken this up so you can look at this in a bit more detail. And again, you don't need to understand it too much, but this signature stuff, the AEV will map to the cryptographic protocol, right? A signature is basically, a CL signature is represented by these 3 numbers. And then we also get a proof of correctness so that we can verify that, yes, this signature was correctly created by the keys that they say they were created by. And again, all correctness proofs have this C thing, which is a challenge. And that's it. And then the last one is just the credential act, which is the holder of the credential storing that information. And this referent is basically the identifier by which the holder can retrieve that credential, the signature on these attributes from their data storage layer. Okay, and the next we're going to have a look at similar output, but for the presentation protocol. So as I see, we're going to see a practical example of presentation protocol happening, under the hood between an exchange of Aries agents. We're going to look again. We've skipped a bit further on in the tutorials. We're at the last stage. So if you have a look here, we're on number 7, which is between a data owner and a data scientist, and they want to authenticate each other based on credentials that they were previously issued by the Open Mind Authority. And what's happened here, the data owners created an invite for the data scientist. And I've copied this invitation across. And again, we have these nice outputs, which have just passed the objects that get sent backwards and forwards between them and outputs them in a way that you can start to look at and see, oh, what messages are getting sent and received. And it's really every time this comes, this like nice handy output, you can see, oh, a message was received from this connection, across this connection ID. The role of this agent that's received the message is prover in this protocol. And the state of the protocol is request received. So we've just received a request for a presentation. We're going to be the prover that's going to fulfill this request. And the request is saying, it's a proof of scientist request. You need to prove it from attributes from this schema. And you need to approve this attribute. And in addition to this, there's a nonce, right? Which can give the issuer confidence of liveness because it's saying, yes, and this proof needs to include this random number that I just created for you. Okay, and then we have responded, right? We sent back, the data scientist has sent back a proof that they are a data scientist based on credentials that they have in their wallet. Again, complex object, basically the thing is to know it's a big mathematical number that can then be put into the Hyperledger Aries type protocols right down the stack. But that information needs to be communicated and exchanged by these two agents, right? It's an interactive protocol. So that means they have to interact, they have to exchange messages. And I think it's real, like that Hyperledger Aries protocols and DIDCOM is perfect for that. Okay, so you can see here, this is just a collection of proofs. And we're basically proving that we have a signature on a credential. Right, and we're going to disclose some attributes and we're going to hide some attributes. And I don't, I'm still learning this object myself and how this works, but I just think it's really nice to see it at least. You can see it, and then you can see that the proofs all get aggregated together. Yeah, it's a load of maths, right? But maths is cool, and the fact that these numbers fit into I'm sending this proof to the other side, right, to the data owner, and the data owner is then able to take those objects, right, and verify them mathematically. So yeah, these are a big chunk of massive maths objects. But the fact that they can be put into a code which implements a mathematical protocol designed by cryptographers and output a value, yes, this is valid, or no, this isn't, right? And there's only one thing that's going to say yes and many things that can say no. I think it's quite mind-boggling in my opinion. So the other side of that is, and you're going to do this yourselves, but we've done it so that the messages come from the other side, right? And this time the role is the verifier. So I'm going to send requests and receive proofs. And again, you can see that the data gets received on this side. Do this what you will. I just think it's a really nice way of seeing how Hyperledger Aries, right, this application layer or this application interface at least, is allowing access to and exposing these really powerful cryptographic protocols down the stack in such a way that it is there if you want to look at it, but also if you don't care or you don't, it's not something that interests you, you can just ignore it. But for me, this was really cool to see. So I hope some people taking this course enjoy this diversion into the cryptography. Thanks.